Ultra-high voltage UHV transmission lines are power lines designed to carry electricity at extremely high voltages, typically above 800 kV AC or 600 kV DC. These lines are used to transmit large amounts of electrical power over long distances with minimal losses. By using higher voltages, UHV systems reduce the current for a given power level, which decreases resistance losses and improves efficiency. They are crucial for connecting remote power generation sources, like hydro or renewable plants, to urban or industrial centers, ensuring reliable and stable power supply across vast regions. UHV transmission lines are defined as systems operating at extremely high voltage levels, commonly above 800 kV for AC and reaching or exceeding 1100 kV for DC systems. The primary rationale for using these ultra-high voltage levels is rooted in the power equation P = V × I. For a given power requirement, increasing the transmission voltage allows a reduction in current, which in turn minimizes resistive I²R losses over long distances. This principle is especially significant for conveying electricity generated from remote renewable energy sites or for balancing loads in sprawling national networks. UHV transmission systems branch mainly into two types with distinct operational characteristics: UHV alternating current UHV AC, typically operating at voltages like 800 kV to 1000 kV. UHV AC networks are suited for interconnected grid systems. They facilitate flexible distribution and are ideal for regions requiring multiple tapping points, branch circuits, and ease of fault management. They must address challenges such as managing reactive power, voltage stability, and harmonic distortions. To mitigate these, series compensation equipment can be deployed, balancing the voltage profile along the corridor. UHV direct current UHV DC is often chosen for ultra-long distance transmission, and it interconnects networks that might be asynchronous or operate at different frequencies. Converter stations. These systems require sophisticated converter stations at both ends. One station rectifies AC power to DC for efficient transmission, while the other inverts the DC back to AC prior to distribution. Advantages: with lower reactive losses and enhanced control over power flow, UHV DC is particularly effective in reducing transmission losses over vast expanses. Detailed engineering design considerations. Designing a UHV transmission line is an interdisciplinary task requiring careful planning at multiple stages: route survey and environmental assessment, site selection. Extensive geographic and meteorological surveys determine the optimal route. Planners study terrain features, population density, environmental impacts, and right-of-way restrictions to ensure the chosen path sustains the structural and electrical demands of UHV systems. Environmental impact. Life cycle analysis (LCA) is commonly performed to examine carbon footprints, ecological disturbance, and overall sustainability. Researchers combine geographic information systems (GIS) data with environmental impact models to forecast and mitigate adverse effects. Electrical design. Conductor selection. The choice of conductors, e.g., bundle conductors, aims to reduce corona discharge and minimize radio interference. Detailed electromagnetic field simulations help in selecting conductor sizes and arrangements that optimize insulation coordination. Insulation coordination. UHV designs require exceptionally high insulation standards. Insulator strings, either of porcelain or composite types, are designed to withstand severe voltage stresses while coping with environmental pollution and UV degradation. Corona rings and field grading. Devices such as corona rings are meticulously designed to manage electric field intensity around conductors, thereby reducing energy losses and preventing premature insulation breakdown. Mechanical design. Pylon and tower engineering. Towers or pylons supporting UHV lines are engineered to handle high mechanical loads from conductors, wind forces, ice accretion, and seismic activities. Structural analyses, including finite element modeling (FEM), ensure that towers maintain precise conductor clearances under dynamic loads. Thermal effects. Temperature fluctuations affect conductor sag and tension. Thermal modeling is integrated into the design to ensure that expansion and contraction of materials under varying weather conditions do not compromise line safety. Materials and component technologies. The performance and longevity of UHV systems rely on advanced materials and innovative components. Conductor materials. Material choices. Common materials include high-strength aluminum, often reinforced with steel ACSR, or even composite alloys that balance electrical conductivity with tensile strength. Research continues into reducing weight while increasing current carrying capacity. Corrosion protection. Coatings and anti-corrosion measures are imperative, given the environmental exposure of overhead lines. This is particularly important in coastal areas or regions with high industrial pollution. Insulators, types and selection. Besides traditional porcelain insulators, modern designs employ composite and polymer-based insulators. These new materials not only reduce weight and cost but also provide superior resistance to environmental contaminants and flashovers. Maintenance considerations. Monitoring for surface degradation and contamination is vital. Advances in remote sensing using drones and thermal cameras allow for predictive maintenance based on real-time condition monitoring. Accessory components, protective devices, ultra-fast circuit breakers, differential relays, and surge arresters are incorporated. These devices are critical for rapid fault detection and isolation, maintaining system stability during transient events. Digital integration. Increasingly, UHV transmission systems utilize digital twins and real-time monitoring sensors, enabling remote diagnostics and condition-based maintenance, which further enhance system reliability. Construction and assembly procedures. The construction phase involves many precise steps that bridge the gap between design and operational readiness, infrastructure deployment, foundations, and pylon erection. Construction begins with the preparation of robust foundations that can support enormous pylon loads. Tower erection requires precision to maintain proper alignment and conductor separation. Stringing conductors. Highly tensioned conductors are installed with exacting standards for sag, ensuring that even under high thermal expansion, they abide by safety clearances. Installation of insulators and accessories. Specialized insulators and corona rings are mounted and meticulously tested to ensure they meet voltage withstand requirements. Commissioning and testing. High voltage testing. Before energization, the entire system is subjected to rigorous voltage impulse tests, partial discharge tests, and insulation resistance tests.